Hello, in this exercise we will show you the effect of reaction wheel and momentum wheel on the satellite attitude. This laboratory is a part of educational satellite laboratory series built, manufactured and designed by Microspace based on NI-ELVIS. After finishing this exercise, you should know the following topics. First, what is the momentum wheel and reaction wheel principle of operation, how to control the satellite using reaction wheel, how to control the satellite using momentum wheel, and finally, what is the difference between reaction wheel and momentum wheel. Here we show a brief description of the mathematical background. Here we have the mathematical model of satellite that will apply to satellite. Also here we have a link to the full documents of the exercise that describe us the mathematical background that we should have to perform this exercise, mathematical background behind this exercise, and the standard simulation figures that should be obtained during this exercise, beside the steps, detailed steps that should be followed to perform this exercise. Then we go to the simulation. In simulation here, as we see, we have a lot of control boxes and figures. For figures here, we have this figure show the generated angular momentum from the momentum wheel. Here, the generated torque from the reaction wheel. And finally here we have this figure shows the applied external disturbance torque on the satellite. Besides this, we have here two figures that show the current satellite attitude, angular velocity and angles about the three channels roll, pitch and yaw. Here also we have a 3D visualization for the reaction wheel, or momentum wheel and the satellite. Here we have a control switch to control which device we will work with now, momentum wheel or reaction wheel. If we select reaction wheel, this means that these bottoms are these control boxes are working with us. Here, the external disturbance torque, the amplitude of this external disturbance torque, and the time for applying this external torque. Here, the reaction wheel generates the reaction wheel generated torque, the period of applying this torque, and the starting time to apply this torque. Also, we can send command manually to reaction wheel manually during the exercise. For momentum wheel, this control box working with us, and this is the applied external torque as we described before, and this is the generated angular momentum from the momentum wheel, the amplitude of the generated angular momentum, and the time for applying this, starting time to apply this angular momentum. So, starting with momentum wheel, we here will apply a torque with 0.01 Newton meter for 10 seconds at the disturbance torque. Then we will send a command to reaction wheel to generate 0.005 Newton meter torque and the positive direction. Here is the external disturbance torque also on the positive direction, and the generated torque from reaction wheel also on the positive direction. It will be applied for 20 seconds and at time starting from time 200 seconds. So we will press start. As we see the effects of applying the external disturbance torque, the disturbance torque applied in the positive direction, so the satellite starts to rotate on the positive direction. At 200 seconds, the reaction wheel works, so it compensates the effect of the external disturbance. As we see here, after applying the satellite the reaction wheel torque, the angular velocity of satellite starts to be 0, and the angles of satellite starts to be constant. If we apply a positive torque to the reaction wheel for for amplitude of 0.001, the satellite will rotate in the negative direction, and this is the effect of reaction wheel. When the reaction wheel generates torque in the positive direction, the satellite rotates in the negative direction, and vice versa. If we apply torque on the negative direction, the satellite will rotate on the positive direction. As we see here, the slope of the angle is positive, angular velocity is positive, as we see here. So generating positive direction from reaction wheel, torque from reaction wheel, this will cause satellite to rotate around in the negative direction, and vice versa, as we see here. Perfect. So now we will work with momentum wheel. Momentum wheel here, we consider that the momentum wheel rotates on the x-axis, and the applied torque will be, applied external torque will be on the z-axis. So we will consider that angular momentum of 0.01 of 1 Newton meter second will applied at time of 200 second, starting from 200 second on the satellite. If we press start, as we see here, the same effect when satellite, when external disturbance applied to the satellite starts to rotate around the z-axis. The direction, the momentum wheel didn't work now. So as we see here, when the reaction wheel, the momentum wheel starts to work to generate moment of 1 Newton meter second, the satellite stop rotating around the z-axis and transfer this rotation to oscillation about the two other axes. This is called the gyroscopic effect. So applying the momentum wheel will neglect the effect of applied angular momentum on x-axis, will neglect the effect of applying external disturbance torque about z-axis. This is called the gyroscopic effect. So as we see here, the difference between reaction wheel and momentum wheel. So the reaction wheel, when the reaction wheel rotates, the satellite rotates in another direction, in the negative direction. When momentum wheel works, it generates what is called gyroscopic effect. This gyroscopic effect neglects the effect of external disturbance torque on the two other axes. So if the applied momentum is applied on the z-axis, the satellite, the momentum wheel can neglect the effect of applied disturbance torque on both z and y axes. So by this exercise, by this simulation, we could understand the difference between reaction wheel, momentum wheel, and actuators on satellite. See you again in different exercises for the satellite attitude control systems and educational satellite laboratory. Don't forget to send any of your comments on microspace.ne. Thank you.